Hello class, welcome to another video for the course. In this video, we are going to study section 4.5, which is focused on graph of logarithmic function. So far, we have learned about logarithm function. We also explored the properties that they have. And now let's study and explore the graph of logarithmic function. So to start, let's look at the graph of exponential function, and then from there we get to logarithmic function, because recall that logarithmic function is just the inverse of exponential function. For example, let's start by 2 to the x. Here in your textbook, you can see the table of data. For the first table of data is for the exponential function 2 to the x. So here is the set of input values, and in the next row, you can see the set of output values. Now, recall that what is a logarithmic function? Logarithmic function is just the inverse of exponential function. So for example, here, you can just switch input and output values to get the table of value for the logarithmic function, log of x to the base 2. Look, just replace, just switch the input output values and you get the log of x. So let's look at their graph. Okay, so I'm gonna just to have, for a warm-up, let's do it by hand, but eventually you don't need to do it by hand. You can use a calculator as well. So suppose you have a graph, or you are looking at exponential function 2 to the x. So what is the table of data? Let's look at the table of data for a couple of values. Your textbook starts from -3 and goes to +3. Okay, so let's us do the same. So we are gonna go from -3 and then -2, -1, 0, 1, 2, and 3. Okay, so these are the input values. Now let's calculate the output value just to warm up. So this is 2 to the x. So this is gonna be, what is the output value? It's gonna be like 2 to the power of -3, right? So that's gonna be 1 over 2 to the +3. 1 over 2 cubed is 8, so 1 over 8. Similarly, we can compute the rest. So 2 to the power of -2 is same as 1 over 2 squared, 1/4. So you can calculate 2 to 0 is 1, 2 to 1 is 2, 2 to 2 is 4, and 2 cubed is 8. Okay, so in this way, we can calculate the output value. These are output values for those input values for this function. And you can also, so you can also plot these points on the graph. Let's also graph. I just want to also put a place later. I want to add a table of value for the okay, here I'm gonna add another table of value because I want to do the same thing for the inverse function. But for now, let me just draw the graph of for, this is x-axis, this is y-axis, and then we look at -3, -2, -1, 0, 1, 2, 3. These are the set. This is the set of input values that we put in the table, and we calculated the output value. So it goes from 1/8 to 8. So let's say this is 1, 2, 3, 4, 5. Oops. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's do it. At 3 is 8. Okay, at 3 is 8. Or maybe I start from the same order. At -3 is 1/8. So at -3 is 1/8. At -2 is 1/4. At -2 is the output is half. And then at 0, it's 1. So it's going to be here. This is 1, right? This is 1, the value 1. Okay, so we plot these points. And then at +1, output is 2. Okay, so this is 2. At 1, it is 2. At 2 is 4 because 2 square is 4. So at 2 is 4. And at 3 is 8. At 3, for the input value 3, the output is 8. Okay. And of course, I mean, we can always connect these points to get a sense of to roughly sketch the graph. So when you connect these points, oops. Right, and we just tried some, but you know that this continues. Okay, so this is the graph of 2x, 2 to the power of x, exponential function. So this graph is for exponential function 2 to the x, and we just tried some of the we just found some of the output value for input value, plotted those points, connected those points, and we got the graph. Now, so this is not new. We already studied exponential function. The goal is to study the inverse function. What is the inverse function? Is log, right? So let's call it G or anything that you want, but we want to study the inverse logarithm of x to the base of 2. This is, since logarithm is just the inverse of exponential function. And in this case, because the base is 2, you see, the base in exponential function is 2, so the inverse also should have the same base of 2. So look, but this is easy. If you want to find the input output values, right? So maybe I just, yeah. So here is the table of value. The way it works is that since logarithm is an inverse of exponential function, just switch all these input output values. So for example, in exponential function, you have -3 and 1/8. Now switch their place. So it's going to be 1/, because it's inverse by the definition of inverse function. So it's going to be 1/8 and -3. You have, in the original function, you have -2 and 1/4. So here is going to be 1/4 -2. In the original function, you have -1.5. Here you are going to have half and -1. You have, here you have 0 and 2, 0 and 1. Here you're going to have 1 and 0. Here you have 1 and 2. In the inverse, you have 2 and 1. Here you have 2 and 4. In the inverse, you have 4 and 2. And finally, the last output value for the exponential function here is 3 and 8. So in the inverse, it's going to be 8 and 3. So now let's plot these points, okay? So let's plot these points. So this is going to be the table of values for logarithmic functions. So this is the logarithmic function, right? We just obtained it by the fact that it's an inverse of the exponential function. Now let's plot these points. So so here the input values are negative, or 1/8, 1/4, half. Okay, so this is half. This is 1/4, and let's say this is half. Okay, and then 1/4 and 1/8. So at 1/8 is -3. Okay, so for 1/8, the output is -1, -2, -3. So it's gonna be here. Okay. At 1/4, it's -2, so it's gonna be here. At half is -1, so it's gonna be this point. At 1, it's 0. So for 1, the output is 0. For 2, the output is 1. So it's gonna be this point. And for 4, at 4, I'm sorry about that. At the next, just a second. Something happened. Just give me a moment. Okay, sorry for the issue. Okay, now we have the graph again. We are on the graph. Okay, so we are plotting the points, and the last point I plotted was here, which is 1 and 0. The next one is 2 and 1. So at 2, it's gonna be 1, so it's gonna be this point. At 4, okay, I need to go further. So let's extend the x-axis. 4, and also I need 8, 5, 6, 7, 8. Suppose this is 8. Okay. At 4, the input is 2, so this is gonna be, it's gonna be here. And then finally at 8 is 3. At 8 is 3. So suppose this is 3. Suppose this is 3. So at 8, it's gonna be 3. Okay, so we use the fact that logarithm is an inverse of exponential function. We switched in the table of value that we had, we switched the place of input-output values. Those are gonna be the points in the inverse function logarithmic. We plotted them. Now let's connect them to draw the graph. We can connect these points. To get, and you know that the table, we just tried some of the input values, so we can see the behavior. We can have a rough sketch of the graph and see the behavior of logarithmic functions. So this red curve is the graph of logarithmic function of, what's the function? The function is log of x to the base 2. So these two curves are the inverse of each other, these two graphs. The blue curve is the graph of 2 to the x. The red one is the graph of log of x. And even graphically, you can see that they are the inverse, because recall the inverse. If two functions are inverse of each other, then their graph is a reflection toward this line. Do you remember? Do you remember we learned that this line, the line of, this is the line of y equal x. Do you remember? So their graph is a reflection respect to this line. Let me make it bigger. Okay, you see that? So even if this is a rough, even though this is a rough sketch, I think you can see that it's like you have the graph of 2 to the x, right? Now, if you reflect it to respect to the line y equal x, then you obtain the red graph. which is the graph of the inverse function. So it's like this line, the line of y over y equal x, acts like a mirror. So the red graph is a mirror image of the blue graph. So these two are the inverse of each other. So this is the way that we obtain the graph of logarithm function. And in fact, in general, logarithmic function has these shapes. So in general, a logarithm function, so when you have a log function to any base, they have, so the general picture is like this, right? So this is the graph of a log function to any base. And let's study the behavior of this graph. So you can see that this graph is increasing, you see. So let's now list the behavior of this graph. First of all, it's increasing. Second, it's concave down. And this is the opposite of 2 to the x, because for exponential function, yes, 2 to the x is increasing, log is also increasing, but 2 exponential function is concave up, but this one is concave down. What else? Let's study the long run and short run behavior of this function. So for long run behavior, for long run behavior of this function is that as you increase the x value, so as you increase the x value, your function is also increasing. So as x goes to infinity, the function is also go to infinity. But look at the behavior of this function around 0. Look, so as you get closer and closer to y-axis, to 0, right? So as you, as x get closer and closer to the 0, to origin, you see, as you decrease the value, so as you approach 0 from right, so you approach 0 from right, what happens to the graph? The graph is going down, and it approaches y-axis, right? So the graph is going down, right? So first of all, the graph is going down, so it goes to negative infinity, and it approaches y-axis, right? But it never cross y-axis. So there is a vertical asymptote, which is y-axis. You can either say y-axis, or you can say the line x equals 0. So this, logarithm, so this is important that you keep in mind that logarithmic function have a vertical asymptote. They have a vertical asymptote. It's like from one side, from the right side, when you approach the y-axis, then the graph is going down, but it never crossed the y-axis. So that's a vertical asymptote. And there is one intercept. There is one another observation here is that there is a horizontal intercept, and that's, look, it's this point, you see, graphically. So the graph cross x-axis at one point, and that point is actually, let me show you in the above example. Look, what is that intercept in this graph? You see, it's this point. It's this point. So the point has the x value of 1, y value of 0. So at 1, at x value of 1, it has the horizontal intercept at x equal 1, which means that the graph cross x-axis at 1. What else? I think these are the main observation. I think your textbook also summarized so here is the graph in this picture, you can see the graph of logarithm of x to the base 2 And here also is the summary of the graph. As the input increase, the output increase. And but it increases slowly, so it's growing, but it's not so fast. The exponential function, let's talk about domain, by the way. So domain and range. So for exponential function, they can take anything. So for example, here, you can see that exponential function can take anything, but logarithm function, maybe I write this here. Maybe I write it here so you can see them side by side. So for exponential function, okay, so for exponential function, domain is everything, right? Domain is from negative infinity to positive infinity, everything. But range, what is the range for exponential function? The graph is located above x-axis. So it's all positive number, only positive number. So from 0 to infinity. It's just it's all positive numbers, right? Now, you want to determine the domain and range of logarithmic function. So for logarithm function, domain, because we switch, recall, we switch the, because logarithmic function is the inverse of exponential function. So for inverse, we switch the input output value, right? So that means we also switch the domain and range. So here, the range of exponential function is gonna be the domain of logarithmic function. So domain is all positive number. And then domain of exponential is gonna be the range. Just switch the domain and range. Okay, and I think from the graph you can also see that for logarithmic function, they only take positive, you see, they only take positive x values, any value greater than 0, but the range can be anything from negative to positive. Okay, so that was the observation about domain and range. What else? Yeah, and here is the long run behavior. Oh, I should add that in my summary here. Yes, I said as we approach to x from right side. So this is one-sided, not two-sided. So as we approach the x value from the 0 from right side, then the function is going down. And you can see that the graph has a horizontal intercept at 1 and 0. The graph has a vertical intercept at x equals 0. The graph is increasing and it's concave down. The domain is all positive value. The range is everything. So we already studied that. And so this is the, in this picture, you see the graph of a 3-log function. So as you can see, the general shape is the same. And now they have a different stretch based on the base. For example, the red graph is a logarithm function with base 2. The blue graph is a logarithm function with base 10. The green one is natural log, so the base is e. So they have the same shape, it's just base kind of depends on what is the value of the base, the graph might be a bit stretched. So now let's do an example. Find the domain. Okay, let's practice domain of logarithmic function. Okay, so the question says log of 5 minus 2x. Okay, log of. Okay, so this is example 1. The question is log of the function is log of 5 minus 2x, right? And the question is, what is the domain? What is the domain? Okay, so again, recall that the domain is that logarithm function. What is the domain of logarithm function? They only take positive values. They only accept positive values, right? They cannot take any negative values as domain. So maybe I'll write down that. So domain logarithmic functions can only take positive values. So that means the input positive values. Therefore, the input must be positive, right? The input must be positive. So what is the input in this function? In this function, the input is 5. The input for the log is 5 minus 2x. So that means 5 minus 2x must be positive. There you go. The rest is algebra. Just solve this inequality. So that means subtract 5 from both sides, then divide both sides by -2. So this is gonna be 5/2. But when you divide both sides by a negative number, right? Recall that when you divide both sides by a negative number, then you need to switch the direction of the inequality. Okay, so that's the answer. That's the domain. Domain is all the values less than 5/2. Okay, so we just need to, the only part that is new is that for logarithmic function, the input must be positive. The rest is algebra. So the answer is anything less than 5/2. From negative interval notation is -infinity to 5/2. Okay, so now let's talk about transformation. For example, let's sketch, so we know the graph of natural log of x. Now let's look at natural log of x plus 2. So you know that this is gonna give us a vertical shift because we already learned about transformation. So whenever you add 2 units to the function, it's gonna be just a vertical shift. Let me explain it from here. Look, the green here, you have the graph of the natural log. It's the green curve. So the green curve is natural log. Now, G is natural log plus 2. So plus 2 means that, okay, now we need to shift the graph. Whatever is the graph, just shift it 2 units up. And I think from the graph, you can see that the blue graph is just the same as the green one, just shifted 2 units up. So that was easy. What about this one? So this one is, okay, I'm gonna draw it, but okay, let me draw this one. Example 3. So the question is about natural log of, this is the function, natural log of x plus 2. So this is, think about transformation. These can be obtained, obtained by natural log of x using transformation, right? So let's first draw natural log. So this is natural log of x. This is ln of x. And this is 1. We know that natural log intersect x-axis at 1. Now, what's going on here? What's the difference of this function with natural log? The only difference is that the input value is added by 2. You see, you have this. It's added by 2. This is the change. between natural log and here. But we know that if inside the input value there is a change, which is addition or summation, that is going to be a horizontal shift. Recall transformation. So this gives us a horizontal shift. Because it is positive, so it's to the left side. So this is going to give us a shift to the left. Shift to left. So we need to shift the graph to left. How many units? 2 units. So for example, look at this point. This point is going to be shifted 2 units to the left. So just drag your curve to the left for 2 units. This is going to be the graph. So this is going to be the graph of natural log of x plus 2. So you see, you can use transformation because you already learned about the graph of logarithms. So you can draw the graph of the logarithm and then use transformation. Sometimes, like the previous example, the shift, there is a shift, there is a vertical shift going up or down. Sometimes, like this one, that the change is inside the input, then the shift is to the left or right. In this case, it's left for 2 units. 2 units. So by the way, let me also mention something else. So our graph has a vertical asymptote, right? We know that logarithmic function has a vertical asymptote. Natural log has the vertical asymptote at y-axis. Now, since we are shifting the graph 2 units to the left, this vertical asymptote is going to be shifted 2 units as well. So from 0, it's going to be shifted to -2. So the new vertical asymptote is this one. Okay, so that means this orange curve approaches this line, but it never crosses it, right? So this is the better picture of the graph. Okay, and you can see the graph here as well. So there is a horizontal shift to the left by 2 units, and also the vertical asymptote now is -2, x equal -2. And now this new graph has a domain of, it takes any value greater than -2. Okay, so now let's do a bit more complicated example that the function is given, the equation is given, and we now want to use transformation in order to draw the graph. I'm gonna show you. I know you can do it by calculator, but drawing by hand is a good practice to study and analyze this graph to get a better sense of these new functions and their properties. So I recommend you to practice drawing by hand. So this is gonna be f of x has this equation 5 times log of -x plus 2. Log of -x plus 2, right? And the question is draw it. Draw the graph. Okay, using transformation, draw the graph. Okay, so look, first of all, what do I see here? Okay, let's name everything that we see. I see the function is logarithmic function, right? And I know that the graph of a log function is something like this, right? That's a log function, log of x. So I'm gonna use, so since the function f contains logarithmic function, I'm gonna see if I can use transformation to drive it from this green curve, the curve of log of x. So what's the difference? What differences do you see between our function f, and log of x? So the first thing that I notice is that it is multiplied by 5. So there is a multiplier here. Recall that this is the stretch factor. So the graph is stretched. So this gives us a stretch. Remember, stretch. This is the stretch factor. So whatever is your final graphing, there is a stretch or compress. What else? Another thing that I see is there is a negative sign. You see, maybe I use another color. So let me clean this up a little. So f of x is 5. So instead of log of x, I see negative x. Let's factor this negative from the input. So it's going to be x minus 2, right? So I'm just rewriting this, right? So I just factored the negative sign. What does this give us? Remember, this gives us, whenever the input is multiplied by a negative sign, that gives us a reflection. So this is going to give us a reflection. Remember? If the input is multiplied by a negative sign, it's gonna reflect the graph respect to x-axis. Reflection respect to x-axis. Remember? I'm just reminding you of transformation that we learned. So the multiplier 5 gives us the stretch. This negative sign gives the reflection. And finally, here I see the input minus 2. This input minus 2 gives us the shift. And this is a horizontal shift, right? The input is subtracted by 2. So because it's subtraction, because it's negative, it goes to right. So this is the shift to right side. How many units? For 2 units. Okay, so there are 3 elements. There are 3 changes here respect to log of x. The input is subtracted by 2. That's gonna shift the graph to the right for 2 units. The input is multiplied by negative sign. That's gonna reflect the graph toward x-axis. And finally, the function is multiplied by 5. That's gonna give us the stretch. So this gonna gives us the stretch factor. Okay, so now let's do it. So I'm gonna, maybe I zoom out. Okay, so maybe I draw a bigger, because this is a small, let me draw a bigger graph to do all these transformation one by one. Okay, so this is gonna be x-axis, y-axis, and then log is this function, right? This is, the intercept is 1, and this is the graph of log of x. Okay, so so first of all, let's look at that reflection. I'm gonna use the same color as I wrote here for drawing each for drawing the corresponding transformation. So there is a negative sign that gonna gives us a reflection respect to x-axis. So just reflect the graph, okay, reflect the log x graph toward x-axis. So it's gonna be like this. Look. So when I reflect this part, it's gonna be something like this, right? So this is negative log x. Oops, sorry. It's log of negative x. The red line is just a reflection because there is a negative sign. So that means there is a reflection toward x-axis, or in another word, x-axis acts like a mirror. So whatever is your graph, now Imagine x-axis is the mirror reflected toward x-axis. Okay, so we are done with this. Now, shift it 2 units to the right. Okay, so that's gonna be, so I'm gonna, by shifting, I'm gonna do it like like this. Let me just so let me see. There is a negative sign here, so that means, okay, let me just make sure we are okay. I'm sorry. This is gonna be a vertical because let me make sure I doing this right. If the negative is, yeah. So suppose we had negative log of x, right? So this is the graph. Now, whatever is the output value, just, oh, yeah. I'm sorry. I have to correct something. I'm sorry, my bad. The negative sign is for input value. The input is multiplied by negative. So the reflection is toward y-axis. My bad. So the reflection is, I'm gonna correct this. Okay. The reflection is toward y-axis. Yeah, that's right. So there is a negative sign here. This negative sign gives us, let me write this down. This negative sign, because the input is multiplied by a negative sign, so that gives us a reflection respect to y-axis. That's right. Because we have the reflection toward x-axis if the whole thing, if the output is multiplied by negative, but because the input is multiplied by negative, so the input, the switch is for input value, from the switch in the sign is for input value, so that means the reflection is toward y-axis. So then the graph should be like this. Maybe. So suppose this is -1. So the reflection is this one. Trying to draw a good graph. So it's gonna be something like this. See, this is gonna be the graph of log of -x, because the domain is multiplied by the input value is multiplied. Yes, so the reflection is toward y-axis. I'm sorry that at the beginning I said the reflection is toward x-axis. The reflection is toward y-axis. So imagine y-axis is the mirror, and then just reflect your graph toward y-axis. Now shift the graph 2 units to the right. Okay, so take this point, shift it to the right. So that means it's gonna be this graph. You see? So draw a parallel curve to the red one, but this one is just log of negative, but x is shifted to the, so this is the blue curve is the same as red curve, is just shifted to the right for 2 units. So we shift the graph to the right for 2 units. And finally, there is a stretch. So that stretch is by 5. So the graph, so I'm going to draw the stretch roughly, but we can also do it accurately. By the way, what happened to vertical asymptote before the stretch? Let me also talk about vertical asymptote. So first, we reflected toward x-axis. So the vertical asymptote, it's still y-axis. But when we shift the graph to the right, the vertical asymptote is also shifted to the right. So it's gonna be from 0, it's gonna move to 2. So this line is the vertical asymptote. This is the vertical asymptote, right? And okay, now do the stretch. So the stretch is gonna just multiply it by 5. It's gonna make your graph something like this. It's gonna make it sharper, right? So roughly, this is gonna be the graph. And if you want to make an accurate picture, you can substitute some point. So roughly, this is gonna be 5 log of negative x minus 2, the final graph. But if you want to, so you have it here as well. But if you want to draw it accurately, then you just need to evaluate it at one of the points, because we already know that it crossed the y-axis at 1, right? Just find another point. For example, in your textbook, it evaluated at -8, and it see that at -8 is 5. Okay, at -8, suppose somewhere is -8 here, the output is 5. So once you have that point, you can connect them in order to have the accurate picture. But roughly, by this transformation, we can see why the graph is like this. So again, there were 3 components using transformation. There were 3 factors here. One factor was 5. The function is multiplied by 5. That gives us the stretch. One factor is this negative sign. The input is instead of x, we have negative x. So that gives us the reflection, which is reflection toward y-axis. And also there is some summation subtraction here that gives us the horizontal shift. So in general, if you use transformation, any kind of transformation, the general format of the resulting function is either in this format, as you can see, it's multiplied by a, that's the stretch factor. And then this input plus or minus something that gives you the horizontal shift, and final addition or subtraction give you the vertical shift, you see? Or if there is a reflection toward y-axis, then you can see that as a negative sign times by the input value. So it's not outside of any of this case. And I don't believe that you need to memorize it, because you already know about transformation. You know, if output is multiplied by a number, that's a stretch factor. If it's added by a number, its output is added by a number, that's a vertical shift, and so on. So I think you don't need to memorize it. You can easily obtain it. So for example, let's do this question, example 5. The graph is given. That's a nice one. The graph is given. The question is find the equation of this logarithmic function. Okay, so let me see if I can. No. Okay. Okay. I'm gonna open a new page to put this graph, and then I'm gonna show you the work here. Okay. So look here, we know that this is a logarithmic function, right? So we already know that this is a log function, right? This because the question says that this is a logarithmic function, so we can have the look. If this is, we can derive it from log of x in another word. So look, this is log of x. I'm drawing it in the same picture, right? So this is log, the graph of log of x. Now, how this blue curve is obtained from this orange curve, but what kind of transformation? So first of all, I see that, look, any logarithmic function is concave down, but this one is concave up. So there was a reflection. So first of all, there was a reflection, because otherwise it couldn't have had, there was a reflection toward x-axis. Oops. Oh my God. Just give me a moment. Okay. Okay, so there was a reflection, because you see that the logarithmic function is concave down, but this blue curve is concave up. So there was a reflection. So let's first draw that, get that reflection. So reflect the log of x toward x-axis. It's gonna be like this. So I'm trying to do the transformation one by one, right? What is this? This is negative log of x. So the red one is just a reflection, of log of x toward x-axis. Multiply the output by negative sign. Okay, now the red curve is also concave up. My blue curve that I'm gonna drive it, that is also concave up. So we obtained something. There is a reflection, and so first of all, the graph was reflected toward x-axis, which gives me the negative sign. Also, the graph is shifted to the left. You see, there is a shift to the left. And how much was the shift to the left? Maybe I use another color. Maybe here. Look, the vertical axis is y-axis. The vertical asymptote is y-axis, right? This is the origin. Maybe yeah, this is the vertical asymptote for log, for the log of x. But in the blue curve, in the blue one, the resulting curve, this is the vertical asymptote. You see? The new graph has this vertical, oh my God, has this vertical asymptote. So this is a vertical asymptote in the resulting graph. So you can see how many units we shifted the graph to the left. For how many units? Look, for 2 units. Maybe I use another color. 2 units. Just look at the vertical asymptotes. The vertical asymptote originally stands at y-axis. Now it stands at -2. So that means we shifted the graph 2 units to the left. Okay, so that's gonna give me, so shift the graph 2 units to the left. Okay, so I'm gonna shift the red one to the left for 2 units. So 1, 0, 1. So it's gonna maybe have to remove this because I don't have enough space. Okay, so now move this for 2 units to the left. So it's gonna come here and the graph is gonna be like this, right? Something like this. So this is gonna be y equal negative log of x plus 2. So now we took care of this shift to the left. We shifted the graph. The graph was shifted to the left for 2 units. Okay. So far, we figured that there was a reflection. So we came up with the negative sign. We figured that there was a shift to the left. So maybe in your textbook, I point them. So we figured that there was a reflection. So we came up that, okay, it must be multiplied by a negative sign. And then we figured that there was a shift to the left. So the input must be added by 2. What's left? You can see that the blue curve stands in a different location than the yellow one. That's because of the 2 things. First, stretch. It seems that the graph had a stretch, and also there was a shift to up. So we need to find that. We need to find those 2 elements. I don't have enough space here, so I'm gonna do the rest in another picture. Okay, so far, so what do we have so far? So far, we know that the graph, the blue graph, right? So far, we know that the blue graph can be obtained by logarithm function, but it is multiplied by a negative sign, and the input is added by 2. The only thing that we don't know yet is that what is the stretch factor and what is the vertical shift. Okay, so we still need to find the stretch factor and vertical shift factor. But that is easily obtained by just substituting points. For example, there are a couple of points here that are easy to use. For example, look at this point, -1 and 1. Okay, so this is -1 and 1. You can just substitute this into the equation in order to, because that's the point of the graph. So f of -1, if you just substitute -1 into the equation, is equal 1. So now you can solve it, because look, you end up with a log of 1 plus k equal 1. Log of 1 is 0. Logarithm of 1 is 0. So that gives us 0 plus k is 1. So k is 1. So we got k. K is 1. You see? So we substitute one of the point of the graph into the equation, and we find that, okay, k is 1, meaning that the vertical, I'm going to rewrite it again. So f of x at this point, f of x is negative. I still don't know what is a, what is the stretch factor, but I know it's a log of x plus 2 plus 1. That 1 gives us the vertical shift. So there was a shift toward up. Now, we still need to find a. So now let's try another point. For example, what else? You may use this point. Or easily you may point 0 and 0. You can also use 0 and 0. Huh? This is also possible. Use 0 and 0. So 0 and 0 is a point of the graph. Substitute here. So f of 0, 0 plus 2 equal, it should be 0, right? So this is gonna give us the a. Do I have a space? Let me see if I have a space to write this down. Yeah, so that's gonna give me negative a. So that's gonna give us negative a log of 2 plus 1 equals 0. So negative a log of 2 equals negative 1. So log of 2 is 1 over, sorry, we want to solve it for a, sorry. So we have a log of 2 is 1. So a is 1 over log of 2. So we got a as well. Done. We are done. So what is the equation of f? So f of x is negative. A is 1 over log of 2. Log of x plus 2 plus k, which is 1. That's the answer. Okay, so I just substitute a into the equation. So there were, let me remind you, there were 4 factors. The negative for the transformation, the negative gives us the reflection of the graph. This is the stretch factor. This is the stretch factor, the function multiplied by this value. This one is the shift to, gives us the shift to left, and this one gave the vertical shift, shift to the up, vertical shift. Okay, if you want, you can also rewrite your function as, so f of x is negative. You can, because you have 2 logarithms, you can, and they have same base, you can rewrite it as log of x. I'm using one of the properties of log, so you can also express your function in this way. So I'm using the property of log. So that's it. So we were able to obtain the equation of this graph from graph of log of function using transformation, and we had 4 types of transformation. We had reflection, we have a stretch factor, we had horizontal shift, and we have vertical shift, and we found each one step by step. And this is the equation of the function, and it can also be written in this format. By the way, your textbook uses, I used 0 and 0, the point 0 and 0. That's why my stretch factor is in terms of log of 2. Your textbook, you substitute another point, 2 and negative 1, right? That's why the stretch factor is expressed as log of 4 here, but it doesn't matter. I mean, it doesn't matter. It's a value. The same, we have the same value. You can either express it as log of 2 or log of 4. That doesn't make a difference. Okay, that's all for graph of logarithm function. I strongly recommend you to practice these exercises, and then when you feel ready, start doing your homework assignment. Thank you for watching this video. I'll see you in the next one.